Hey there, you the viewers. Today in this video I'm going to be talking about how we get the even and odd components of the fast Fourier transform equation. And to start off doing that, let's go ahead and recap a little bit on the DFT equation. Now we all have seen this in a couple of different forms, and it can be altered a little bit depending on what application you want to use. And the fast Fourier transform is a mathematical algorithm that basically you can calculate a sample DFT much quicker than taking the actual DFT to get to that particular sample. So the reason we find our DFT equation in this form here is because we want it to be compatible with the radix 2 FFT pattern. And there's a couple of different FFT algorithms, like a radix 4 or a prime factor, various different things. But for case in point of this video, we're going to do a 4-point example using radix 2. So our first goal of the FFT is to come up with the FFT equation. And to do that for radix 2, we have to break down our DFT equation up here into two smaller components, an even component and an odd component. So in order to do this, we're going to have to first look at this attached term over here, which I've written down here. Now, let's go ahead and reassign this variable with another name, and he probably looks rather familiar to you, or even if you haven't seen him yet. This is actually a twiddle factor, in which case, this little r up here will be our DFT sample that we want to take, such as our first sample or third sample. And this bottom, which you'll notice all the blue K's happen to be the same, are equal to the number of points for your FFT or DFT. So in this case we're using 4 points, so you'll notice all of these little guys have a 4 on them. Okay, so now we have it on our real and imaginary plane unit circle, and as we all very well know, this position corresponds to a 1, this one to a j, this one a -1, and this one to a -j. Okay? So, relatively simple if you think about it that way. So, let's go down here, and our next step, we'll define g of r as the DFT, and it's going to be equal to the summation of our same DFT equation as up here. But we'll notice that down here, we're only using our even components. And the way we get about doing that is we let k be equal to 2 times m. Whereas to find our odd components down here, our h of r, that are only odd, we're going to find the same thing, except we're going to add 1 to the end of it. Okay? So let's move on to our second page. Using the complex conjugate symmetry, which is a property that all real FFT, or I guess you could even derive it from real DFT, when you take a sample, any sample you take in this world is real, you're going to end up with a complex conjugate, and they're going to have symmetry to them to prevent any imaginary roots. So if we look up here, what that does to our FFT equation here is that all of our even components loses its twiddle factors because they end up just being 1 or -1, whereas all of our odd components keep and remain a twiddle factor because it'll have some imaginary component to its actual value, but when we multiply it later on with our value of the odd component, they actually cancel out, leaving us with only real components. So that was a brief explanation on how we get the even and odd components for our main FFT equation.